So this is the fourth video in the Programming Layers of Abstraction series, and specifically in the retro game Get Off My Head portion of this. Last time we left off, we were looking at this code. We'd just gotten character-to-character collision, which broke apparently both jumping and falling, and the collision isn't very good. So let's take a look. We were last looking over 10, so we'll take a look at 11. We have the shebang line, the imports, the global size, Pygame STL, initialization on the screen, the caption, the mouse is visible. We load up the SF sprites, which are let's see right here, these sprites. We load up the background, which is this. We load up the mask, which is this. We create two characters, pulling their sprites out with an offset. So this character for the first, this character for the second. We create a background surface, fill it. We have two positions of the characters, which are associated with the names of the surfaces, the images. We have a left and a right position so that characters could move left or right. We have the jump velocity, which is 0 unless they're jumping. The fall velocity, which is 1 since gravity is always affecting things. In this version, we've added our first class. So this is the first instance of object orientation in this series so far. So previously, no classes, just a couple functions, and the rest of it all imperative code running straight down from the beginning of the script. And now we've introduced our first class, which we're calling actor. And in Python, you initialize a class with this underscore underscore init underscore underscore method. And a method is just a function inside of a class. So it's really the same thing, except it differentiates it mostly by era of programming. They were calling them functions when they switched over, when everyone switched over to basically thinking object orientation was the right thing to do, to differentiate calling them functions and calling them functions that are properties of a class. They called them methods. So that's some of the background there. In Python, you pass in self as the first argument, which allows the class to maintain its own state. The state is maintained through the self variable, which is always there. Passing in an ID, which you can see here it's highlighted as a Python keyword. You shouldn't do this, but I did it anyway. Python allows you to do it. It's just not good form because this is a built-in function. Anyway, there's an ID, there's a name, there's a starting position, there's the image right, image left. So these would be the two surfaces that I do here. So here I flip them. This would be image right, and this would be image left, which is flipped from image right. So I'm passing in some kind of ID, a name, a starting position, and then the right and left image. Now I save all this information to self, like I said before. This self variable is the way that you contain all the information of a specific object, and an object is an instance of a class. And if you don't understand object orientation, this isn't the right place to teach it. So you should go look up on Wikipedia. There's tons of books on it for your specific languages, whichever language you work with. But this is how it works in Python. The actor is the class The self will be the particular instance of that class, and since we're passing in information in this method, this function that's associated with this class that initializes the class, we're setting all of these values into self. And here we set some additional values. The jump and fall and move left are also set into self. So here we had them in globals right here, and now we're moving them into this class. And the thing about classes is that it allows you to take one section of code here, just this, and then use it to create multiple sets of things here where it contains all this data. So there really is a lot of powerful wrapping going on, in that we can take all this stuff that was here loosely identified by just names, and now that we've given it this actor class, it's all in this self data here. And then this, of course, can be assigned into a variable, and you can access all of these they call them member variables, just like functions are member functions, and we call those methods. So that's the basics of imperative object orientation. And so here we have this actor, which is the first time we're starting to wrap this into a more modern construct, late 80s, early 90s modern construct. Moving out of the 60s and 70s, we're now in the 1980s and 90s. So here we have this actor, and then here what I do is I create a list of actors. So there's going to be some number of actors, and I first create actor 0. So I'm assigning it a real global variable, but then I also append it into the actors list. And here you can see I don't do that with actor 1, which is probably a mistake, but maybe not. So I assign it an ID of 0, and I give it the name of Ryu, and I give it the starting position of 300, 130, and I give it the image right of guy 0, and the image left of guy 0 left. And I do the same thing here with Ken, with a different position, a different ID, and then the guy 1 and guy 1 left variables. So this should probably be here, but it isn't here, so I'll just leave it out for now. I'll probably fix it in the next version. The scrolling offset, this is the same. This is the top left position that will scroll at X, because the screen is the same size as the map in the Y dimension, so there's no scrolling in this dimension. Here we have the test collision by pixel step. It doesn't look like anything is necessarily changed here. So here's something that changed. Right here in move position collide, we've added this actors. And let's just double check this. I'm making an assumption it didn't change, but it might have. So we'll test it with the page test. So flipping from one to the other, they're the same, only the line numbers change. So I go down one page and down one page. Oh, is that not? Oh, that's the problem. The cursor wasn't actually on this. So down one page and down one page. And now distance X, still no changes. And finally we come to here to do the final test. And still no changes to that variable. But we can see that this move position collide, this is totally new. So we used to have move position collide with scene, but move position collide is completely new. And what it changed is it looks like here I have pause move, bounding box, scene image, scene color, log. And here I have pause move actors, so this is new. Bounding box size, scene image, scene obstacle color, log. So my guess is what I did with this is I used this new function which includes actors, and I got rid of calling this one directly, and now I call this one, and I probably pass in this actors list right here, and this is probably why I only added this one, because this is actually the non-playing actors list. So when I move my character, I don't want my character to be in there. There's another way of doing this, but I think this is what I was doing, is this actors list only collides with actors that aren't my character, and my character is this second character here. So let's take a look at what this does. First, it tries to collide with the scene, so it says scene pause after we call this move pause collide with scene, and as we know, that will either be this position if we did collide, or it will be this position plus the x and y out of the array, the 2-item array or 2-item list from this move position. So if the scene position and the original position are the same, then we know we collided. Otherwise, we didn't collide with the scene, so scene collision is false. So then we test to see if we had actor collision. We start out assuming it's false. We put our target position from our original position, adding with move, just like we do with the move position collide with scene. Then we create a rectangle out of that by using the target position and the bounding box size, which we pass in here, the same way that we pass in here, which is essentially the image size. Then we loop over all the actors, which are all the actors not including the actor that we're controlling, because we didn't add them. So I have an additional test in here. This is actually not very accurate, because one, I'm not checking the ID of the actor, which should be unique, or even the name, which could be unique, but I'm checking the position, which doesn't necessarily indicate uniqueness unless I just don't allow that to happen. But if I say teleported some character to a position, these two actors' positions could be the same. Anyway, I loop over the actors here, so this is going to go over each of the actors in that actors list, which I only put one in if I pass that particular one in. So then I look to see if they're not the same, and if they're not, here you can see it skips the self. And if they're not, I say I get the rectangle for the given actor. I create that using the Pygame rect, the actor's position, and the bounding box size. And then I do a test collision with the built-in rectangle Pygame method, collide rect, which tests the actor rectangle with the target rectangle, and if there's an overlap, they say that they have collision. And then I say if they have collision, one, I print it out for debugging, two, I set actor collision to be true, which reverses this actor collision as false. And if we did not have collisions with the scene or actors, return move position. So if we didn't have either the scene collision or the actor collision, return the target position. Return the target position. Otherwise, return the position that we were started at. And in Python, what this list does is this was already a list, but I'm returning a new list because if I modify this list, it will actually modify this value because Python passes references around to specific contained data. So this allows me to change this data later on without it affecting this data. So you'll see this in Python anytime you want to keep original data and not modify it. So let's just make sure that this hasn't changed, just to be aware of it if it has, and this has not. And there actually is a number of changing here. But my guess is I might have just deleted all these comments out. So here I'm just cleaning things up. So if we look, this is all we do is has collision, final position, else, final position, target position, and return. And here, same thing. If has collision, final position, else, final position equals target position, return, final position. So this is all the same as this. I've just cleaned it up. So this just got cleaned up, and there we go. Now we have this get scroll position. Did that change? Nope. And here, I used to have this code underneath the draw function, and now I moved it to the top, and eventually this is just going to go away because now we've got this actors. So probably I moved it here as I was copying this data, so I wanted to remember that I had this here, and this, here, and this here, so I moved it up here just as that, just so I could look at it while I was working with it. And then we finally come down to the game loop, which is here. We know there's going to be some changes. For instance, I start off by creating, by telling myself where all the actors are, which I didn't used to do. That's just kind of debug information. I've added a comment here for this being enemy AI, but comments don't really matter. And you can see that I changed a number of things here. So instead of move position collide with scene, it now calls move position collide, which is what we investigated earlier, the new one. And this one adds in the actor position list. So here, I'm creating this each time from both the characters. So we do need to test that you don't collide with yourself here, because this will collide with yourself. So why I created that actors list and then never used it and never included the guy one position, I don't know, because I wrote this 2 years ago. But here we can see I create the list every time, and I pass it in, and it does include my character. And that means that I pass in the same values for the enemy AIs, which have this entire actors list, that I pass in with my character. Here I pass in the sprite size, they're all the same. The scene mask. Now, at this point I also had jump in the past one, or the previous one, so now we're jumping still. This looks the same. And this looks the same, it's just changed to the move position collide with scene to the move position collide, which wraps move position collide by scene, and then also adds the actor comparison. We do the quit event pump, and the difference between the character handling is also the same, just doing the wrap. The fall is also the same. The jump is also the same, so just more of this wrapping. Escape to hit exit. Here's the scrolling of the world. That remains the same. And finally, all the rest of it remains the same. So what that gets us is this. We have this obvious bug right here while that guy is probably jumping, but only going up one at a time, because he's both jumping and colliding. I don't understand why when I move I can't fall, but that must be some bug which we'll probably find that I fixed. And that's what we've got. That's what this version is. So on to the next version. The next version has obviously fixed the problem of sliding up things, so we'll find out what that bug was. We got stuck up there. So it's imperfect for sure. But it's much better now. And the characters collide with each other. Let's get a horizontal collision going here. There we go. So characters are colliding with each other. They collide with the scene. They don't get stuck quite so much anymore. And let's compare the difference there and see why. So we have the shebang, the Python imports. At this point, we're adding in another global for scale, 0.5, which I didn't used to have. And I'm using the scale instead of doing divide by 2. I'm using multiply by scale, which is actually cleaner in my book because 1, you can't get into divide by 0 problems, and 2, I think it's just a little more straightforward. Not that either of them is very difficult, but this has a ratio to it, where divide obviously by 2, it has an inverse ratio. So this is a more forward perspective on this change. So anyway, we do the Pygame SDL, we load the sprites, we load the background and the mask, we still do the surface for the guy 1 and guy 0, we create the background. Now we've gotten rid of this thing that we had here, where we had the globals, so my suspicion that this was just to keep this data around. Looks like it might be correct. We might have gotten rid of it this time. So now we're starting to clean up. So we're seeing some of the global variables go away. And in terms of abstractions, having global variables is seen as worse than having local variables or having wrapped variables like classes and object instances. But the important part to understand why is that you can't control the sprawl. It's like inside this actor, I can have all of these variables and I can create any number of them. And when I create them, they're contained within the reference, a single reference, where here I have to have a different variable for guy left, a different variable for guy 1 and guy 0. And so just the sprawl of things will create scaling problems that you don't have, that you try to avoid by wrapping things. You still have the same amount of data that you have to track, but the question is how many labels you associate with it. And the more labels you associate with it, and the more reference places in the code you have to go update to make changes, the more complex it is as a lifecycle management of the code. And so that's where working with wrappers like classes works well, because if I want to add one more variable here, I don't need to go and change it to every one of these guys, or if I want to set the default from jump from 0 to -1 or something for some reason, I can do it just in this one place here, and it works in all of the actors. I don't have to find them, and they might not even all be in the same file. Whereas if I go find the actor definition, I can get them here. So cleaning up global variables and moving them into contained into containers such as classes or even modules, which are different Python files in Python. So here we can see this this actor class is expanding out a little bit. So it used to be just, oops, it used to be very tiny, just this one small thing, and now it is bigger. I have this __ RAPR, and just like this init that has underscores in front and behind it, this is a special Python method, and it means that if I print this, this is what comes out of printing. So I print out the ID and the name of the character and the position every time I try to print out this actor. And so this is a convenience method for not having to do this separately, and it saves quite a bit of space and makes it quite a bit easier to make detailed textual representations for this data, because you see I get 3 pieces of data here, which I can use to understand which data I'm working with in any given place in the code by just printing it out. So And this also gets called, anytime that the object, which is the instance of this actor, gets turned into a string. So it can be embedded into other print statements as well. It's not just a print-oriented thing. So here I have this GetSurface. So now I'm actually working with this data that I passed in here. So here I have image right and image left. And now I'm saying get the surface. And I say which one I'm going to get is based on whether it has move left is true or false. So if move left is true, then it returns the left image. If it's false, it returns the right image. So now we're using this data that I passed in from the initialization and the defaults, and we're coming up with how to get like the single image I had. So this wrapping this means that this can now become much more complex over the future. We could have different things for looking up or looking down, and that can all be contained inside this of which surface we're going to draw, and all we need to do is ask the actor object to get the surface, and the logic for which surface to use we'll figure out which one. And this would be the same as if we had animations and we had the character actually like walking with the legs moving back and forth. We would be able to determine where in the animation they were, whether they were pointing in different directions, and then choose the right image for them since we're doing this image-based animation. And that can all be wrapped inside this GetSurface method. And so that again shows an ability to wrap what would normally, when we normally were doing this, we were doing it in this imperative, straight running down fashion like this. So we would have to keep putting tests. Like here, we have to have tests for each one of these things. I have to test this, then I have to test this, then I have to test this for falling. This can all be wrapped up so that you don't see this copy and paste. So if I had two enemies here, I'd have to copy and paste this entire section here. But when you put it inside of a method in a class, then the object that instantiates that class only needs to implement one method, and you don't need to duplicate that. You just need to call the method. So this is another way of it's not hiding complexity, it's arranging complexity so that when you apply a label to it, you only apply this one label. And then when you think about it, you only have to think about this one label. And when you inspect it, you only have to come to this one place because this is where the logic is. So moving on, I'm creating an update function, which also didn't used to exist. And this is going to take care of some of this other stuff. So here, I'm calling it actor instead of self, just to make this a little clearer. And this is going to take care of trying to fall. And if you notice, it uses this move position collide, and then it uses this global variable actors. Now, I don't see actors being set here, but because this hasn't been called yet, it doesn't actually need to be defined. It can be defined later on. It just needs to be defined before it's invoked. That's why Python is a scripting language, and that's called a strong-typed late-binding scripting language. Strong-typed meaning that you can't add an integer with a string because they're two different types. So it treats the type strongly. Late-binding means that it doesn't do static type checking. It finds out which types they are when it actually goes to run them. So it doesn't know what this is, or most of these things, until it goes to run them, and then it actually inspects them inside of its internal data. So here we've got the jump. If we're not jumping, we look to see if we can fall. It's the same logic we did before. I've just moved it inside this update function. Now I have if jump is higher than 0, then I do this. And so if we look at it, I'm not handling left and right. I'm only handling up and down. So this is now taking care of the up and down of things, if I'm jumping or if I'm falling. So this update is just what I'm considering to be physics and not behavior. So I'm not trying to do something. I'm just handling rising up and going down. So here's where I create that global actors. And again, notice it happened after this. In a lot of languages, this isn't allowed. In Python, it is. You just have to know your language and then work within it. Here you can see I did finally append this in. So I create the actors, and now I've given it an uppercase. And generally, because you don't use very many global variables and you want them to be specific, one method of doing that is making the entire global variable name uppercase, which I normally never do, like this. So these are both global variables, but the difference of them is this one is actually going to be used globally, and this one I'm just creating essentially to pass into this actors list. I could actually just take this and put it into this append, but it makes it a little harder to read. It's easier to read if I assign it to a label, a variable here, this reference, and then I put it here, and then later on, afterwards, I do the actors append. And I do it again for the Ken character as well. This is the scrolling offset, no change there. Test by pixel step. My guess is this hasn't changed, and it hasn't. Let me just verify. No change. So this top part doesn't change, but let's take a look at move, position, collide. Now we had that bug there, so this is going to have to change at some point. So let's see what's changing. For one thing, I've moved some stuff around. Instead of I used to pass in the position and then the move and then actors, and now I'm passing in the actor. So I'm not passing in the position anymore, I'm passing in the actor, which contains all that data, including position. So this is how I'm replacing out going from single global variables that track something like a position to the actor object, which tracks everything inside the class for that instance of that object. And then how far we want them to move, and then a list of all the actors, and then the scene image, which will be the mask, and the obstacle color and the log, and these are the same. So now we go to move, position, collide with scene, and what changed again is now instead of providing it just a regular position, I provide it the actor position, which is the member variable inside the class object instance actor. So then we're going to move, and then instead of just giving it a bounding box size, which I pass in the actor image size. So now if the actors actually had different image sizes, that would work. And so now we've gone from having one variable that we're making an assumption works for all of these into being able to have different ones, and the power of wrapping that data into a class allows that to work because of this dotted notation. I can have a different image size for every actor, and the reference for the image size through the actor remains the same. Whereas previously we could only pass in this bounding box size, and it forced all of them to be the same size. Otherwise we would have had to deal with that differently. Finally, the scene image remains the same. Everything else remains the same on this line. So I do the scene collision test, which is the same. I'm going to come down here. One of the things I'm looking for is that bug that stopped movement from working, falling from working. And obviously we added that update function, which takes care of jumping and falling, but it looks like it does the same code, it's just wrapped it. So we should be able to find a bug here, and I'm saying it up front because when I find it, that was one of the goals. And if you just happen to stumble into it and you didn't have it as a goal, then you really didn't accomplish anything, you just stumbled into it. So to accomplish something, we'll set the goal of having to find that bug, and then we'll see if we can find it. So testing against actors. So I have this actor collision, and now I have a new, and so this is false, this is Boolean. And this one is set to none, collision with actor. So what I'm going to be doing here is I'm going to set the actual actor object that I collided with here. Right now it's none, but if I set it to something, it will be a reference to that actor object, and then I'll know a lot more about that actor object than their position. I'll also know who they were, and I'll know their ID, and I'll be able to look at a number of things about them because I have, or in fact, everything about them because I'm storing all of that in the actor class, and so I'll have their actor class object instance here. So we have the target position where we use the actor position and move. This actor position is the one that we're passing in. This is the actor to move. Target rectangle, we use Pygame's rectangle to create this, and again we use the actor image size, so it is their actual size. Now we loop through all the actors and we call it test actor to test, and we say if the actor ID is not the same as the test actor ID, which is a much better way of doing this than if the actor position is not the same as the test position. This is the person we will be moving, and this is the one we're testing. So this is a much better way of doing it. Here we are only going to really skip ourselves and not skip someone who happens to be overlapping us. So here we test the actor rectangle, which is the same. We use the Pygame rectangle test. We find that we have a collision. Done. If we have a collision, we set it so that the collision is true. We stop printing this out anymore, probably because I solved the problem. And then we set the collision with actor to be the test actor. And this way now we know who it is. Here, if we didn't have collisions with scene or actors, return move position. So this is standard. But look what I've done here. I've changed this return value into a tuple. So it actually returned two values. Unlike before, we only turned one value, this target position. So now I return the target position and a collision with an actor. And then if there is no collision, I return collision with an actor no matter what. So even if there was no collision, this just returns none. But I'm returning the same value that I return here if we do have a collision. And here, because we had a collision, I don't move. And so again, I return the list. So it's a new position. So the X and Y are in a new list and can be edited. Here, this is already a new list. I created it earlier, so I don't need to worry about it. There's some debate. People think it's bad style to return more than one value in a function, but Python allows this. And so that means it's really up to you whether you think it's actually messy or not. One problem you can have is if you return two values here and three values here, now you're starting to create problems for yourself because you don't know how many values are being returned. Sometimes this is normal, like if you do a regular expression, the regular expression may return zero values or multiple values with embedded values, and you have to test all of those. But that's kind of like a data scraping, data extracting function, whereas this is not a data scraping or data extracting function. So you wouldn't expect to have different amounts of values, different count of values, but here they're not, they're the same. And then essentially what you're doing is you're comparing, would returning just a raw tuple, raw two values of this be more complicated or less complicated than creating a new type of object like a return object that packs both of these variables in and then returns that. So now we'd have another class that we need to do, and we'd instantiate that class, and we'd pack it with these variables, and then we'd return a reference to that class, and then we'd be able to reference the variables that are inside that class. So the trick is when to do something like that, when to wrap this data and only pass in one thing versus passing in two things. So if your language doesn't allow you to do this, you don't have a choice. You have to pack them in. Now, but if you do have a choice, you could say just passing these two things is pretty simple. Creating that class means now I have to track the class, know about the class, read the class when I'm looking through the code. Then I have to take a couple lines to put it in. So just to show you what it looks like, it would look like this. So we'd see like a collision result, and then we would have something like this, and we would say yep, like that, and then we would say self pause equals pause, and self collision with actor equals this, and then here we would do something like this: collision result equals collision result with target pause and collision with actor. So then I could do this and then return result. So this is what I'd have to do instead of this line right here. And so look at all these extra lines here. So I've got 4 lines of definition and 1 line of invocation. So it's 5 lines instead of just the 1 line that I was previously going to have. Now, I reuse some of these. I would reuse it for this one as well, but then I have to know about this. I have to pay attention to it, and I just think at this point it's not worth it. Once it gets more complicated, that's where it starts to become worth it to wrap that sort of stuff. But otherwise, I don't have a problem returning 2 variables. So this is the kind of stuff that you have to think about when you are trying to balance complexity, and there can certainly be, this can go overboard. If I start having, more variables that I'm passing back, this is starting to get a little crazy, especially if I only pass back this many variables down here. That's too much. That's too much craziness. So then it might make sense to have a return container. The other thing you can do, of course, is you can do things like this. You can return a dictionary, where dictionaries could have any number of elements in them, and you could have target position equals target position, and so on. But now you have to deal with the fact that you've got this, which is a looser form of a variable container, but you still have to inspect all this stuff. It's not free for sure. More complexity, just in a different place. So this takes care of the changes to move, pause, collide, and I didn't see the bug yet that stopped that made the weird stuff happen in version 11. That made that happen. I haven't seen that bug. So now I move down to move, pause, collide with scene, and I expect this will have not changed. And I am correct, it did not change. And then we have the get position scrolled and the draw. And these don't look like these have changed, and they have not. Now I've added a different thing. So here I've added player actor ID equals 1. You have to actually go up and look at where the actors were defined to know what that actor ID is. But this is here, actor ID is 1, and that's Ken. So an interesting thing about this, now that I've set my player actor ID, it means I can change that player actor ID anytime I want to. So previously it was hard-coded. I was set it so that guy 0 was the enemy and guy 1 was the character that I moved. And I had all of these different lines here that referred to guy 0 and were doing the enemy AI. And then I had all these lines here that were dealing with the guy 1 position. So in one line here, now I've made it dynamic. So this global variable tells me which of the actors' IDs, which I could change at any time as well because I've only specified them in this one line right here. So which of the actor IDs is the one that I'll be controlling. So I could change it. I could add more of these. I could make it, it could be the 10th one, so I can switch from the first one to the 10th one. It even makes it possible for this to be dynamic, so I can change which character I'm playing in the course of the game without quitting and restarting and editing the source code. So here we have player actor equals none, which means initially I don't know who it is because I'm making it dynamic here. This player actor equals 1. So I start looking through the actors. This was that global list that we just were referencing. I look for this particular actor. If the actor ID is the player actor ID I just specified here, then I set this global variable to be the player actor, and I stop looking. Breaks out of this for loop. So if the player actor is none, then I throw an exception, and it's another WTF exception, like how did I screw this up? That means that I didn't specify an actor ID that is 1 when I was creating actors, and that creates a problem. So then back down here to the game loop, which is here. 46 minutes, so we're getting close to normal time when we wrap this up. Classes have definitely made things move a little slower during the introduction. So this is going to change a bit this time. For instance, previously I was just looking at guy 0 here. There's only one actor, and there it is. So now I've changed this so that it's just looking over any number of actors. And what it says is, if this actor is the player actor ID, then continue, which means to skip this actor in this for loop. So if there's only one of these, it wouldn't do anything. But since we have 2 actors in here, and only one of them matches this actor ID in player actor ID, then we'll only do the single actor, which used to be this guy 0. But instead of having to hard code all this stuff, so that I would have to copy this out and then change this to guy 2, and then change this to guy 3, and change this to guy 4. And if I change any of this logic, I'd have to change it here, and here, and here, and here. So instead of having to do that, now I've got this one loop where all of this happens right here. So if the player is to the right, the player actor, and again, I know who the player actor is because I just set it right here, this global variable. And now I'm referencing their position, their X position, from whoever this enemy actor is, and they'll move towards it. They'll, it's the same thing that we did before, but instead of it being hard-coded like this, it's now more dynamic in that we're doing it in this loop, and we're using this known global player actor to point to the object, which has the position and all the other information. So we do the same thing here. And notice this is just left and right. The physics is going to be left to that update, which we haven't invoked yet. The event pump for quit. This handles the left, right, and up for the actual player. And you notice I just say player actor jump now and player actor pause. So I've gotten rid of the guy 1 references here, again making this more dynamic. So I've moved from having specific labels that not only had one specific label like player actor or actor, but it had guy move 1, guy move left, guy 1 pause. It had to reference the guy 1 image, the guy 1 left image. All of these individual labels that are not associated with each other are now associated with each other inside this object and can reference any of these variables together, making it much faster. So you can see the improvement in the complexity by being able to wrap them, because now I don't have a bunch of loose variables that need to all be updated or managed as individual labels. I have a single label that then gives me access to these sub-labels. So it's instead of just having a bunch of paper strewn all over your floor, you put it into an individual filing cabinet, and anytime you need papers of that particular type, you can go to that filing cabinet, and if you buy another filing cabinet, you can put different papers in there, and you know which one to go into. So this is the beginning of organization. And there'll be a lot more of this that we go into as we get further along. This is just the introduction to these things still. So we have, this is where the physics happened. We go through all the actors, enemies, player character, doesn't matter, and we run update. And this handles our up and down. And I still haven't found the bug, and I think I'm at the end. So we do our quit, we get our screen scroll, and my guess is, let this change a little bit. How did it change? Screen scroll to X, boundary X, screen by pixels 3. Here I'm drawing the scene. I'm doing this test to see move left, or if it's not move left, we draw the right picture. Otherwise, we draw the left picture, and the same one for this. And now when we move over here, I just go over the actors, and I just say draw, and I say actor GetSurface, and this handles whether it's going to be right or left. And then it draws to the background with the actor's position. And so all of this used to be this. And obviously, if there was more characters, it would sprawl out of control. There would be tons of this stuff. So, reduction in lines, in vertical space, in number of symbols that you have to process, and in, I could have an infinite number of actors, and this will never get bigger, whereas this is going to just keep getting bigger and bigger and bigger. So we're really seeing the advantages now of this technology, being able to put things into lists anonymously, not having global variables, not having loose variables that have assignments only with guy 0 left and guy 0. This versus just having an actor and then knowing image left and an actor image right. This is much weaker. And so you can see how it was simple that we started with this, but you can also see how much more powerful this is. So again, when you're creating something, you need to think about, at the moment, what do I need? And then long term, what do I need? And come up with a compromise of what you can get out quickly and then what's going to help you later on. So when you get fast at this stuff, you don't even think about adding, these classes. You just do it, and you do it in a simple way, so that later on you don't have to deal with all of these loose labels that you have lying around in your globals. And you can do really cool stuff like this, instead of much more complicated and sprawling methods like this. So this wraps up this code, and I didn't find the bug there, so I'm not going to make too big of a deal about it. My guess is it had to do with the update function fixing the falling, because I must have been not falling when I moved, because if you notice, it also happened when I moved off on my own, that while moving, I was not falling. So I must have screwed that up somewhere, and I just didn't catch it when I looked through it this time. But it's not too big of a deal. Obviously, I caught it before. I would have been nice to point it out. So this is what we'll be going to next. Now, I'm still the red character here, but there's so many more characters jumping around. You can see they're blocking each other. They're in each other's way. They don't all seem to be following me. They seem to be dealing with each other a lot. And now you can really see where the name of this... I got close enough that guy started following me. And then it kind of threw them all into a little fit. So you can see where the name of Get Off My Head is coming from, as everybody is constantly landing on each other's heads. So this will be what we look at next. So this was the fourth video for the programming layers of abstraction, and I will see you next time to get a little bit more detailed here and start turning this into an actual game. Alright, see ya.